Good evening, everyone. My name is Dennis Wong. This video is going to be about my project presentation for MC13 on digital circuit modeling using HDL. So this project as a whole is the design modeling and also verification of digital circuits using HDL. And we will perform a simulation using EDA Playground. And this video, I'll be going through my design for the firmware and also my simulation results. So the first digital circuit today is a half adder circuit. So basically, a half adder takes in two inputs and it produces two outputs. In this case, when one of the inputs is one, we get one at the sum, and when both of the inputs are one, we get a carry out. So this is a typical behavior for half adder, as you can see for the simulation results. A full adder, on the other hand, is basically as two cascaded half adders. So the behavior is very similar. For a full adder, it has an additional input signal called the C in. So C in is the carry in from the first um, to the first adder. Okay. So when the all of the input signals are one, in this case, 1 + 1 + 1 equals 3. So 3 minus 2 is 1. So at the sum, you get 1, and then you get a 1 as a carry out. So that's why the output is 1, 1. Okay, so that concludes full adder as well. Um, okay, so the ripple carry. So in this case, we have a ripple carry adder 4. So it means that we have a 4-bit ripple carry adder. So the behavior of this adder is also very similar, okay, to the previous one. Um, Four cascaded adders, full adders. And we are just going to find one simulation. Okay, for example, the second simulation here, when input from A is 1 and input from B is 15, 1 + 15 equals 16. But note that we are dealing with a 4-bit output. The maximum is 15. So because 1 + 15 equals 16, we have to it overflows and then we get a carry out of 1. Okay, so this is the behavior. Moving on, we have an 8-bit adder slash subtractor unit. We are going to provide the mathematical proof. There are two scenarios, okay? First scenario is when A plus B, and oh, by the way, the behavior, so either adder or subtractor, it is controlled using a third signal called Cin. So when Cin is equal to 0, the whole circuit behaves like addition. So 120 + 120 equals 240. When Cin equals 1, we have to subtract uh, B from A. Okay, but we don't actually perform subtraction. What we do is we invert the bits of B. Okay, in this case, we get the binary of B, invert it, call it B prime here, and then we exchange it back into the decimal representation, which is 135, and we add A, B, and also the C in. So 120 + 135 + 1 equals 256. And remember, we're dealing with an 8-bit here, so it overflows. And then when something overflows, we get 256 minus 256 equals to 0. Okay, so that's why we get 0 in the end. And it is the same thing as 120 minus 120. Okay, so this is the circuit itself, and then the simulation results. Let's skip this and just look at the simulation results. So you can see that here the scenario just now, scenario 2, C in equals 0, equals 1, 120 minus 120 equals 0. Moving on, we have the functional block diagram of a subsystem called DPU. It has three submodules: ALU, debug interface, BCD 7-segment to decimal. This is actually an interface between to a se seven segment LED display. So the whole tree of the submodules itself will be related to this but they are fairly straightforward. Most of the stuff, okay, all the implementation is hard coding. So for example, BCD is the integer, okay, we want to be displayed at the seven segment. So we have a mapping between the integers and also the individual LEDs to light up at the seven segment display so that we get a particular number. Okay. So in this case, for example, to get 8, we have to light up the LEDs described in this case. Okay. Um, right. So the ALU fairly straight similar as well. ALU is a multi-purpose arithmetic logical unit. It can perform addition, subtraction, or multiplication, for example, based on the this signal called ALU op. Okay, so for example, over here ALU op is 4, and then for 4 we are doing A in minus B in. A in this case is 7, B in is 4. 7 minus 4 equals 3. So this is the simulation result for this module. Moving on, we have debug interface. So debug interface basically is very similar situation to the previous module. We get a D out, okay, and this D out is actually determined by whatever DSEL that we have chosen. So in this case, if we look at the last signal here, 1 1, so default is selected, and then we get 5 zeros and then ALUOP. Okay, so at this stage, ALUOP is what? 4. So 4, and when we get the D out is 4. Okay, so again, nothing really special about this, and the entire simulation in this case just combines all of the three modules and then perform a simulation to module. So if we look at the simulation for DPU module, let's take a timestamp, okay, at time equals 60. At this point, the SCL is 1, 1. And so the D out would be a combination of 5 zeros and ALOP. Sorry, ALUOP. And if we look at the ALUOP, it is assigned D in the 10th bit to 8th bit. So if we look at the D in here, 10th bit to 8th bit is 3 zeros. So the D out would be a total of 8 zeros. So this is the simulation result for DPU module. Um, Moving on, we have a module called M1, and M1 basically is quite similar to the previous some of the previous modules. The output is determined by what we this select signal is. So if we look at one of the cases here, when SEL equals to 0, okay, at this point, uh, what we have here, 1 0 at the front and in 2 at the back. In 2 is what? 1 1. So 0 1 1 equals 3. So our result is actually 3. So that is the M1. And then we have register 8. So register 8 is a D register. It takes in an input, okay, and then whenever the control signal enable is asserted, then it will just get this input and then just transfer it to the output. So that's what register 8 does. You can see from the simulation, this is exactly what is being done. LDP is the control signal. At the positive edge of the clock, LDP will be transferred to this P here. Okay. Shift, sorry, Shift L register 8 basically is a register that very similar to the previous register 8, but it also has another feature, which is the shift left. Another control signal it has called LDSH. So when the enable, okay, the control signal enable is asserted, if it checks if LDSH is asserted as well. So if it is asserted, what it will do is basically similar to the register 8, but if it's not asserted, it will do a bit shift. Uh, so it takes the original data, shift it to the left, okay? And then at the least significant bit, a shift in bit will replace the least significant bit. Let's look at the simulation result. Okay, so this is the data. We call it D. So it's this number right here. And then at this point in time, shift in is a 1. And when LDSH, like we mentioned previously, is not asserted, it will be shifted to the left. And then the shift in bit is 1. So this whole sequence right here, shift to the left, 101, 0010, 101, 0010, and then the shift in bit is 1. So 1 at the back. Um, Another module is the shift right register 4, very similar to the previous shift left module. Instead, in this case, it will shift right. Again, very similar. When the LDSH is not asserted, enable is asserted. Shift in is 1. And then if you look at the previous data, 1101, shift to the right, which is 110, okay, 110. And the shift in bit will be added to the MSB. Shift in bit is 1 in this case. So 1110. Finally, we do a simulation for DU. So DU is a combination of the three modules I mentioned previously, shift left, shift right, and um, register 8. It is actually from this DU module. Okay, basically, uh, it models this behavior. The simulation is done in tranches. Okay, so because we have to see the behavior at different levels to verify that it works. But the point of all of this is to see that, is to verify one relationship, which is P equals to P plus A. Okay, we get all of the data up until this point in time, and we get the P of 20. So this is 20 in binary. And if you look at the behavior here, when PSEL equals 1, LDP equals 1, A will be it will be added to, we'll add with P, and then the result data P, will be added back into P. So if we look at the simulation result again, A plus P, 20 plus 20 equals 40. And then 40 will be put into P. And this is exactly what we get. 00101000 is 40 in binary. Okay, so like we mentioned here in the comments, this is exactly what the behavior is doing. That's the circuit is doing, and the simulation provides the exact behavior. So this simulation result is correct. And with that, I would like to conclude this presentation. Thank you very much for watching. Um, if there are any questions, I'll be ready to address them. And once again, thank you very much for watching.